Hello, my name is José Javier Aguilar Fuertes, and I'm going to introduce this work for SOCO 2020. This work is titled Following Vortices in Turbulent Channel Flows. During this presentation, first I will introduce the problem, then I will briefly describe the algorithm we developed to solve this problem, and last I will show some of the results obtained by the program developed. First, we have to note the importance of turbulent losses in energy consumption. It is calculated by Jimenez et al. That approximately 5% of the total carbon dioxide generated by humans can be attributed to losses in the boundary layer. This boundary layer is determined by the Navier-Stokes equations. These equations have no analytic solutions, represent chaotic phenomena, and the only insight that can be obtained to these equations is by means of experiments or numerical experiments. The DNS, direct numerical simulation, that has to be performed in simplified geometries, will have very large computational costs, both in time and in storage. First, these results were analyzed by means of statistics, by calculating the statistical properties of the result, but with new computing power that came in this century, a new approximation was developed. This approximation consists of tracking aggregated phenomena in the flows. These aggregated phenomena can be of dissipation, that are vortices, or of momentum transfer. These are large Reynolds stress events, also called sweeps or ejections. And here in the right we can see a isosurface of the vorticity on a flow. So in line with this new trend, we have developed an algorithm, the objective of which is to detect and track vortices and Reynolds stress events in very large datasets that are the results of those DNS simulations. There are some problems to the development of this algorithm. That is that both vorticity and Reynolds stress events are very multi-scale phenomena. They are not constrained to only one range of sizes. Due to the sizes of the datasets, parallel computing is needed, and the storage must be handled very efficiently. So the algorithm developed takes a DNS time step as an input, and first applies a structure recognition and then tracks in time the vortices to return the lifetime of the vortices of all Reynolds stress events. First, the input data to this algorithm are the steps of the DNS simulations, which in this case have been turbulent Poiseuille flows in up to Reynolds 1000. These are in structured meshes, but all DNS must be in structured meshes, so this is not a constraint to our problem. These simulations have been done with the LISO code that is based on the formulation by Kim, Moyne, and Moser. It has the advantages of only transporting two variables, and it is a spectral method. That means that the domain must be periodic. In this case, the domain is periodic in Z and X in the graph in the right hand side. To determine whether a point is relevant for our clustering or not, we have to fix a criteria. For vorticity, the Chong criteria, as modified by the Lalamo, has been chosen. And for Reynolds stress events, the absolute value of the variation of the velocity. Both criteria need a minimum, so this minimum has been calculated by means of a percolation analysis. Once the input data is ingested, the structures in the flow field must be recognized. First, the domain is divided into slices perpendicular to the main direction of the flow, in which every slice has a set of points that are above the criterion that either belong to a vortex or to a Reynolds stress event. These points are clustered and connected into coherent regions that are in the image of the middle, colored, every coherent region in a different color, and these coherent regions will be a graph will be a node in the graph that we are constructing. To construct this graph, we construct the edges by connecting every coherent region with the coincident coherent regions on the planes forward and backwards of every other plane, taking into account the periodicity. Once the graph is fully constructed with nodes and edges, as can be seen in this image, the connected components can be reconstructed. The connected components are the sections of the graph that are only connected to themselves. So every connected component in this graph will represent a vortex that is only connected to itself, so a coherent structure. In the image on the bottom right, every color represents a different coherent structure in the domain. Once in the image shown here, the graph has been reconstructed to 3D space, and every structure is a different color. Once the structures have been recognized in the flow field, they have to be tracked through time. So to do that, a weighted norm comparison is performed between every pair of vortices, one from the previous time step, one from the current time step. To do that, a calibration is needed. This calibration needs to set a weight for every factor, that are volume, center of mass position, and bounding box dimensions, and a bias. These bias and weights are set by means of a nonlinear optimization problem. That is a kind of training for our data. This operation, this weighted norm, can give two outputs, that if the similarity is greater than the bias, then it's a pass, and we can say that it is the same vortices. This is usually happening for vortex or structures that do not change much during the pair of time step. In the right hand side there is an example. Or if they are not, if the similarity is lower than the bias, it's a fail. So we cannot certify that it's not the same structure. We need to make a more in-depth analysis. In this case, a point-to-point comparison that is computationally intensive, as all the points in a structure are tested to the other points in the previous time step. But only 30% in this case of structures needed this comparison for every time step. The objective here is to reduce as much as possible the amount of structures that need this point-to-point comparison, and then that is why the team is now developing an approach based on feed-forward and LSTM neural networks. On the right-hand side, a graph is shown for the lifetime of a small vortex in the steps that the evolution is linear or very, very small, and that the error is bounded, but in the steps that something happens, either it joins to other vortex or it separates, the errors are greater. Once the tracking is done for a series of time steps, the lifetime of a vortex can be analyzed. It can be analyzed how it is created, how it dies, the evolution through the flow, if it divides into smaller pieces, or if it incorporates other structures to make a bigger one. In the right hand side, an example of some of these process happenings is displayed. Last, the code presented was used to track a sweep and ejection and the vortices that surround them, and it is presented in the video here. These are the references used for this work, and thank you for your attention.